Ever's mission is to enable a delivery of competitive green energy on demand at scale. No competing solution does this. Coal and natural gas are not green. Wind and solar are not available on demand. And hydro and geothermal are not truly scalable. To move beyond partial intermittent solutions, we need more than wind, solar, and batteries. We need Everloop. Ever fills this need by taking a niche energy source, geothermal, and finally makes it scalable by eliminating the need for volcanic temperatures or permeable aquifers. Ever does this by leveraging advances from North America's shale drilling revolution to mine heat directly at scale via conduction rather than by producing a fluid from an aquifer. Ever mines this heat by creating what is essentially a radiator kilometers below the surface, composed of the effective equivalent of up to 100 kilometers of hermetically sealed wellbore. Our IP is how to implement, operate, and configure this radiator in a safe, scalable, and cost-effective manner. Key elements of this IP are: first, we connect two horizontal wells, toe to toe, kilometers long and kilometers deep, to create a large U-shaped well that is then made closed loop as a tieback pipeline on surface. Closing this loop then creates a thermosiphon effect that eliminates the parasitic pump load of 50% or more that typically blocks low-temperature geothermal projects. Capital efficiency is then massively improved by drilling multiple laterals on the same vertical well pair. Adding a second well pair back to front creates a daisy chain effect that recycles any waste heat and eliminates the pipeline at surface. Using our proprietary technique to seal the wells without any need for casing the laterals further improves capital efficiency. Finally, as Everloop is a true closed-loop solution, we are able to dramatically improve efficiency by the use of proprietary working fluids. Some of our initial implementations of this IP focus on niches as diverse as electricity in Japan, heat in the Netherlands, and combined heat and power for isolated off-grid communities. These and other large early adopter markets support energy prices sufficient to ensure high Everloop profitability right from the start. Later, based on volume production and our future product roadmap, Everloop will ride the cost curve down to wide global applicability. Having documented every step of our solution via our patent suite, Ever will be the essential global partner for any operator or service company in this new trillion-dollar market for green baseload power. The future truly is.
Future truly is. Yeah, fine. So we won't talk about that method. It's kind of a disruptive technology that's come in. It's different a little bit from what we'll talk about in conventional EGS and conventional geothermal, where physically the fluid contacts the reservoir and is the heat transfer agent. And in this kind of innovatively, but maybe difficultly, they use horizontal drilling, very long separations, 5 kilometers between wellhead to wellhead, so a very long loop, just like the length of the loops in ground-sourced heat pumps, and also that it's cased, and so there's no contact of the fluid directly with the rock. So there's no seismicity, there's no fluid losses that have to be replenished or fugitive fluids into the aquifer. The first one of these is installed already in Rocky Mountain House, which is in western Alberta, just north of Calgary, between Calgary and Edmonton, in the Rockies. And apparently it works. What's surprising to me is that it works, because as we'll go through this course, we'll find out that the rate controlling process is, if it's conduction only into the pipe, then that's a relatively slow process. So the ability to be able to recover heat at scale is limited by that. But I guess what helps this system along is that the separation or the length of the pipes and the number of pipes that you have are actually very long. And so the residence time, there's very long residence time. So you could run it in the daytime when you need to use the power. You could let the fluid be stagnant at night to pick up the conducting heat into the fluid and then recover it. And so that's kind of an interesting technology. I think Ever or Ever, I can't remember. It's one very specifically. So anyway, we won't talk much about that, but it's there in the background just as a curiosity. The other thing I was going to just talk about was the Tonga again, just because I thought it actually bears. So with the EVER system, you may have noticed that they're 3,500 meters down, 3.5 kilometers. So certainly at Rocky Mountain House, that would be at the low end of our 25 to 50 degrees centigrade per kilometer boundary. So at 3,500 meters, we would be at something, probably about 100 degrees centigrade. So relatively warm, almost boiling. You can, of course, boil other fluids in binary plants, as we'll see. So you could generate electricity for it. But I think it's used for direct heat rather than for generating electricity. So sorry, we'll look at that. We'll maybe examine whether that's feasible or not. It's all proprietary stuff, so it's all kind of not very open, but it still seems a little strange to me. But it may well be that the 5-kilometer spacing is what makes it viable. We were talking about the Tonga eruption. Of course, news is coming in on that it cut a trans-Pacific internet cable, so there's no communication going on very much between the places, so there's very little news is coming out. But this was kind of a cool graphic from the BBC. And so this is what it was like when it was erupting. You can see the plume. It collapsed looks like a slope failure, so it left just the two islands, top and bottom, and the material in the middle of it disappeared. So the crest of the volcano was now below sea level, apparently by 100 meters or so, they think, and that was what actually blew. So the contact of the hot magma with the ocean, apparently it's a Goldilocks spot, not too deep. If it's too deep, then the pressure of the ocean will suppress the escape of the volatiles, the dissolved water and CO2 and sulfur that's present in the magma. And if it's above surface, then it just becomes an effusive eruption. And so this was after the explosion. And so these two big islands on the top have degenerated into two little islands and some other blocks in between. And so the graphic of what was going on, and actually this is, if you can hear this is just amazing to me. If you listen, it's like a rifle shot. That is, it's not physically it's an explosion. And so what happened across that was, I thought this was basically geometry. So it was a volcano, it failed, it went a couple of 100 meters below the surface, contacted that after it removed the stuff from the top part of the volcano, contacted with water, exploded, and removed all the components. And you can see the before and afters. And I thought there was a different one. Yeah, okay. And so the interesting thing relevant to this course, well, obviously it's relevant in that we've said already that the locations of major heat flux on the planet are at plate boundaries. This is on a destructive plate boundary. And also, we have been talking about other things. It's amazing to me that the shock wave for this was actually heard in the UK. It was picked up by infrasound sensors. So infrasound sensors are placed worldwide to pick up noises, the spectrum of noise, specifically for nuclear arms deterrent type things for aerial tests. And it was picked up, and the time it took to travel is congruent with 300 meters a second, 600 miles an hour, which of course is the speed of sound in air. And the other thing which is interesting is that obviously the big question in Tonga is the tsunami. If you're close to the eruption, you don't get much lead time to it, but the arrival times of the tsunami that developed are roughly the same as in other places. So what was it in here? It was 10 hours, well, obviously Fargo's inland, but roughly 10 hours to the US, and it's 11 hours to the US, 10 hours to the West Coast. And so that means that the tsunami is traveling pretty much at the speed of sound. So it's traveling at 300 meters a second as well, which of course you can calculate because you know the speed of the celerity wave from 303 is square root the depth of the ocean times gravity. And I haven't done the calculation, but the ocean's between 1 kilometer. The deepest ocean is probably 6 kilometers deep, Marianas Trench, I'm thinking. And so you can do that calculation. So I thought that was kind of curious. So that fits in with kind of what we're talking about today in terms of sources of heat, because obviously the plate boundaries where Tonga exists is one of the places where you would have high heat flow. Okay, all right. So what do we know so far? Well, we've made a couple of points. I guess we know that around the world there are locations where we have high heat flow. They're on constructive, as in the Mid-Atlantic Trench, and destructive, Mid-Atlantic Ridge, destructive, the destructive plate boundaries on the west coast of the US, etc., and at hotspots like Hawaii. We know the order of magnitudes of that heat flux is of the order of 100 milliwatts per square meter. Well, I was going to look it up and I didn't get around to it. So you've taken solar classes. What's the insolation from the sun? Is it in Nevada, is it 1,500 watts per square meter, or is it 1,500 milliwatts per square meter? Watts? I thought it was, yeah, okay. So that makes the other point is that the heat flow from the Earth is completely trivial compared to the insolation that comes in from the sun. And that means that the thermal flux onto the surface of the Earth is the temperature of the Earth is completely dominated by the incoming thermal flux. And so the temperature of the Earth is set by the nighttime and daytime heat, which will be maximum and minimum temperatures. As you go down deeper in the Earth, as we'll find, maybe to 6 meters or so, it damps out, so it's roughly the middle of those magnitudes. So in Pennsylvania, if the wintertime temperature low is 25 degrees and the summertime high is 85, 90 degrees, whatever the middle of those is, it should be about 55 degrees Fahrenheit, because that's the groundwater temperature around here in this part of the continent. And so that is set ultimately by insolation, with geothermal conduction making essentially a very small contribution to that. 3 orders of magnitude less, right? 150 milliwatts versus 1,500 watts. So actually 10 to the 4, right? So we talked a little bit about conduction and convection and what the schematics of them are. So what I want to do today is talk about how we accommodate heat flow in the crust. So the basics of these two forms of heat flow, we talked about conduction and convection as we have here. I'll switch to this. And I was going to make these larger actually, but not. And so we can try and understand exactly what's going on. So if you've taken heat flow class, then you'll know that heat flow is governed by Fourier's law. My terrible handwriting these days is getting worse, but hopefully you can make it out. And if you look at the individual components, this is a heat flux. This is in watts per square meter. This would be the same as the heat flux that we're talking about from the Earth. Thermal conductivity is lambda. Temperature change over distance is the thermal gradient. And so physically what that means, if you took a core of rock, you have an upstream temperature on it, T1, downstream temperature on it, T0, so you have delta T given by this. It has some length attached to it. This would be dx. This would be dt, the difference in temperatures. And if you know this physical coefficient, the thermal conductivity, which is in watts per meter degree Kelvin, you can calculate exactly what the thermal flux would be. You can do the unit check, of course, which you should, by putting the appropriate numbers in it. This is Kelvin, this is length, and therefore when you look at that, it's watts per square meter. And of course, milliwatts per square meter would be a thousandth of that. And so that's part of the key equation, but it's not enough to be able to look at it in a more sophisticated way. So if we look at steady state conduction, we can use Fourier's law, and we can probably estimate transport from that. But if we want to look at transient conduction, so we're going to put a cold fluid into the ground, we're going to have it flow through the rock, and we're going to attempt to take heat from the rock and put it in the fluid, and then take it out of the rock as a product. So heat is water is our heat transfer agent. So what we need to do to look at the transient behavior is to look at the transient equation, and we use conservation of energy. And so if you think back to your past, conservation of energy says the flux of heat in or out of a control volume plus the net accumulation of that heat has to be zero. It's a conservation equation. This here is equivalent to what we've just said is Fourier's law, which is dt dx. This has a minus sign because the heat flow is in the opposite direction of the gradient. That's all that minus sign means, because we want to use thermal conductivity to be a positive constant. It's just easier that way. And if we substitute this for heat flow in the x direction, we end up with, for a one-dimensional heat flow equation, we can do it in 3 dimensions, but for a one-dimensional heat flow equation, we get this. This is the specific heat capacity. It's written below, I get, but I'll write it anyway. And for water, it is, well, it's written down below, but so we'll talk about that. This is the density of the medium. And so it was a rock, and it's static, and the heat is moving through it. Then this would be the density of rock, 2,700 kilograms per cubic meter. If it was water that it was conducting through, then this would be 1,000 kilograms per cubic meter. We sometimes call this the diffusion equation because it accounts for the diffusion of heat through the system, diffusion of temperature. And so those individual components, we got some numbers for them. We looked last time to see that rock thermal conductivities is of the order of 1 to 10 watts per meter per degree Kelvin. Water was roughly slightly temperature dependent, but of the order of half a watt per meter per Kelvin. Densities, I just stated, we have those. And we have magnitudes of heat capacities, which we can get at constant pressure or constant volume. We're usually interested in constant volume. I'm not going to worry about this, but we'll deal with that. So in other words, so what is heat capacity? I think I write it later on. Water, you know, right? And for rock, I think it's something like, say 1,000. It's written further down in these notes. You can probably scroll. If you have these notes and you're using them, then you can probably scroll down to them. So, not that it matters. They're just numbers that we use. So another thing that we can do, often we can do, is we could take this equation and we could divide both sides through by rho c. And if we do that, then we get a parameter which is called thermal diffusivity. And actually it's a dimensional constant, but it's a trick we can use to kind of non-dimensionalize equations, just like Buckingham pi. It's a very widely used method in engineering to codify equations. And thermal diffusivity is in units of meters squared per second, length squared over time. And a good number to remember for rock, it's mentioned later on, is something like 10 pi meters squared per year. And I realize that's not SI, but often we're interested in figuring out what fluxes would be per year. And so not a bad number for lambda over rho c, which we're going to call, unfortunately, uppercase K, kappa, not to be confused with Kelvin, of course, is for rock. So anyway, so some parameters written down here. I guess I've written those things, but they're written down here. So some parameters that we can use in this expression. So that's for conduction. So that requires that this medium is not moving in any way. And so that's certainly true when we look at the crust, because this is where the heat is coming into the system from the mantle, the molten mantle below, and it's conducting here. And so I guess if you looked at the temperature profile with depth, even though we like to draw Z as positive upwards, then the temperature profile would be this 25 degrees to 50 degrees centigrade per kilometer. And so this is Z. And so you could think about this if you wanted to. And you could just do Fourier's law, I'm not going to do it, on a vertical column. And you'd use, if you went down 1 kilometer and 0 kilometers, then this presumably would be 25 degrees centigrade or 50 degrees centigrade, depending on the gradient, delta T. This length would be 1 kilometer. And if you use the magnitude of the thermal conductivities we had, you should come out with something like some tens or hundreds of milliwatts per square meter. So that's kind of the deal here. And so that is in this little, just to put it in perspective, that is in this the crust here, which is 70 kilometers deep. This is 410 kilometers, 660, center of the Earth at 6,000 kilometers. So this is just this skin that floats on top of the mantle. And we can expect that conduction would occur in that. We said also that conduction is the most inefficient form of heat transfer. Convection is much more efficient. And we can think of convection in 2 modes. We can think of convection in the mantle, where the molten rocks are turning over in the subsurface, and the actual fluid that's moving is the molten magma, which we'll refer to as free convection of the mantle. But we can also think about free convection in a porous medium. So if you like, you could have a reservoir, petroleum reservoir or a fluid reservoir that's heated from the bottom, and the fluid that gets moving is the water. But the water, different from free convection in the mantle, the water is flowing through either fractures or the porous medium, which is static. And so we can look at both of those cases. And what we can do is we can characterize the likelihood that convection will occur, these currents will be set up, is dependent on something called the Rayleigh number, after Lord Rayleigh, the scientist from, I don't know, 1700s. And the Rayleigh number if you're in the UK, is the ratio of the buoyant forces. So as the material heats, it expands, it gets less dense, and therefore it wants to buoy up. And that motion is resisted by the viscous flow that it has to move against some other static fluid in trying to get up through the system. So when the buoyant forces are large compared to the viscous resistance, then convection will occur. And a number for that to happen is typically, for a Rayleigh number larger than about 1,000, is the initiation of convection. And that convection is a function of a number of components. So this is the thermal expansion coefficient. And this for solid rock is about 10 to the minus 5 volume per degree Kelvin. Sorry, I'm writing over this. So a very small number, but it's volume. So it's a change in volume per unit volume. Always positive as you heat, it gets larger. And that is a measure of how much its density changes, right? If it gets larger, it's still the same mass, its density has to reduce. An average density of the fluid, so for molten rock, this would be 2,700 kilograms per cubic meter. Acceleration due to gravity, the temperature difference between the top and the bottom of the cell. So in other words, if the temperature here was 0 degrees centigrade and it's 50 degrees at a kilometer, this delta T would be 50 degrees centigrade. And the depth over which that occurs, D, the viscosity of the fluid, which is resisting flow, and this is the thermal diffusivity. So this is what we've already said is the ratio of thermal conduction to density times specific heat capacity. And we know all numbers of those. And so that's what allows us to be able to get convection. And so the kinds of things that we'd get, let's see if I can do this. This is just an HTML thing. I don't think it opens if I just click on it. No, it doesn't. So this, close this. And so the idea is that the behavior is something like this. You could heat something from the bottom, you'll develop convection cells, and so you get these animations of exactly what these cells would look like. They're typically equiaxed, kind of square in form, just the geometry that gets set up. Rayleigh number, which we just talked about. And the idea is that these cells would look something like this. And so as you heat from the bottom in this top figure, if you heat from here and cool from the top, then you'll develop these cells which self-organize, and they self-organize over time so that they're roughly equiaxed laterally and vertically. If you look at what the temperature profiles are within that, then you see these plumes rising as they're buoyant. They cool at the surface. There's a downdraft of the cooled fluid, and it sets up this motion. So it's pretty straightforward. And so you can imagine them looking at like this in 3D. This is a 2D picture, but in 3D, there'd be a central core that rises, falls off to the side, and the downdraft at the side is in harmony with the second cell that's right adjacent to it. And so that would happen in the mantle. So that's not of super interest to us. But what is of more interest to us is what the convection might be in the crust, where fluids can actually move. And so the idea is, if you take the swimming pool or the saucepan that you've been boiling on the stove, it will have convection currents set up in it. If you fill that saucepan full of water up with sand and then keep on boiling it, then that water, just like the magma on its own, will convect through the porous medium. And we can convert the same non-dimensional parameter, the Rayleigh number, to that by realizing now that the resistance to convection is by not the viscosity of the fluid going through the structure itself, but by the fact that it has to go through the porous medium. So it's the permeability of the porous medium that makes a difference. So what we can do is in the original Rayleigh number, we can replace this term, the d squared term, with permeability, which we really haven't described yet, but it's in meters of units of length squared. And if we do that, we have a Rayleigh number, which again has to be of the order of 1 to 3,000 for convection to happen, which is the thermal expansion coefficient, the temperature differential, top to bottom, the distance, top to bottom, gravity, density of the fluid, in this case, viscosity of the fluid, thermal diffusivity of the fluid, the fluid in this case, and one extra parameter, which is the permeability. And the permeability can vary over, from 10 to the minus 21 meters squared for shales to 10 to the minus 12 or 9 for open fractured rock. So it varies over maybe 10 decades of parameters, so it's widely variable. And this is the main parameter that controls what's going on. And so you can get convection best if you have a high temperature differential, a short, thin layer, a thick layer, a high conductivity, or to make it, this would have to be small to make this large, a small viscosity that doesn't impede flow, and a small magnitude of thermal diffusivity. So all of those will allow this to happen. And of course, we haven't talked about this yet, but ultimately what we're really interested in is what we'll refer to as forced convection. I put one too many I's in there, I guess, but that's okay. And the idea of this is this. If this is our reservoir, and the temperature in that reservoir is something. So if you look at the temperature as you go across the reservoir as being some magnitude. So that's typically what our reservoir would be. You go into it, a horizontal reservoir, geothermal gradient is vertical, and so if you go horizontally, the temperature should be the same. So now what we'd like to do is we'd like to set up a pressure gradient across this. And the pressure gradient across it would be something like this. And the idea is that that pressure gradient would be you injecting a fluid at some pressure, having another borehole over here where you reduce the pressure. And so maybe the pressure in the system started off at some intermediate value. You raised it at the upstream part to be able to, by injection, and you depressed it at the downstream part by recovery, sucking it out. And so you set up this pressure gradient. And now this flow of the water through the sand that's in the pot is convecting, but it's forced convection. It's forced by the pressure differential. It's not being by buoyancy. And so this recovery of the fluid will allow us to be able to say, will allow us to actually take fluid out from the bottom end. So a flow rate would be Q, which would be equal to meters cubed per second. And so this would be allow us to be able to say something about how much power we'd get out of that system, because I think we said in our second meeting that the mass flow rate multiplied by specific heat capacity of the fluid that's flowing multiplied by the temperature differential. So that is the temperature within the reservoir and the temperature outside the reservoir, which is air temperature, which you flash the water to make power, is governed by this equation. And so the larger this magnitude of mass flow rate, and of course mass flow rate is just Q multiplied by the density of water. So this is the convective, forced convective flux. And the heat rate that we get out is going to be the product of this flux and the temperature differential. And you remember we also said that all three of these parameters have to be finite and big for this to be a big number. If one of them is small, such as if your mass flow rate is really fast, but you can't pick up enough heat as you travel through here, then delta T would be small. It would be the same as the injected fluid temperature. And even though the flow rate would be high, your heat output would be nothing. And so that's the key issue that we have to address in this class. And of course, that's the key issue with the EVER problem, right? How do you get enough heat surface area to be able to recover heat from those very long boreholes? Maybe feasible, not sure. All right, so we've talked about the distribution of thermal resources. I'm not sure we need to go back to this. We've made the point that the schematics of what's going on are these constructive boundaries, mid-ocean ridges, melt is applied. It doesn't push the plates apart, but the plates fall apart. And the plates fall apart mainly because a constructive boundary over here is attached to this descending slab. And the weight of this descending slab is like pulling on a pulley that pulls the rest of the plate over and pulls it down. And so it's pulled by the slab that moves it. And so these get slightly pulled apart. Maybe the pressure of the melt inside also pushes them apart. The crust is very thin, and so there's high heat rate. Not very useful geothermally because there aren't very many places where those are present, not on the ocean base. Iceland is one of them, one of the very few, I think. We have destructive boundaries where crust is fed back into the mantle and melts at depth. As it goes down, it dehydrates. The water that's in it boils off and rises. That water aids the melting of the initial crust by lowering its melting temperature, melts the crust and allows that crust itself to rise as volcanoes. So convection occurs within the crust, much more effective than the conduction of heat that occurs here everywhere else. And we also have hotspot volcanism such as Hawaii, as we talked yesterday. And so we mentioned that these are just plumes that come up and rise as a hotspot in the crust above a moving crust. The plumes are relatively static. They're part of the convecting system of convection cells that we've just looked at the kind of video of on the website, Columbia website. And these plumes stay static as the crust moves. And so Hawaii now is directly underneath one of these plume hotspots. The islands to the east were previously there. And so the crust is moving to the west. Originally they were above that hotspot. They've moved towards the west. The main island, the big island, is there now and is being built up. In time, that main island will move across, the plume will stay constant, and another island platform will build. So those represent places where we potentially can recover geothermal energy, preferably on the surface, right, rather than being on the seabed. So we don't need to deal with that. If you look at locations around the world, we looked yesterday at North America. If you look at the same, you can look at places where you might be expectant that you have some decent chance of picking up geothermal sites around the world. So the mid-ocean ridge goes down through Iceland. Actually, it goes through the Reykjanes Peninsula down here, I think, but that's good enough to make the point. And so this is the ridge which is spreading in both directions, either side of this, and opening up. And so Iceland, for a very small country, is easily able to supply energy for the whole island, both as distributed district heating, warm, direct use power, but also generate electricity for it. There were plans to run their fishing fleet on electricity or hydrogen recovered from fuel cells from hydrolyzing water using the electricity. There are big aluminum processing plants. Alcan, I think, is present on Iceland because electricity is cheap. Bauxite comes in, aluminum ore comes in and is processed with the cheap electricity there. So this is a constructive plate boundary. If you look at the Soultz project, Soultz-sous-Forêt, on the border between France and Germany, this is the Rhine-Graben. The Rhine-Graben is what we talked about last time as a rift valley. If you take the crust and you pull the crust in two different directions, then what you develop is it snaps, and as it pulls apart, you get a block of this moving downwards along these breakage points as you stretch it. So if you stretch it out in the direction of the arrows, this block originally was at the surface and it's dropped down. So this is a valley due to rifting, and this allows magma to come up in this area here and to be relatively high within the surface. So the Soultz project in Europe, sponsored by the European Union, been going for 30 years, still not commercial, but it is productive and it produces some small amount of electricity. A frozen plate boundary runs down the center of Italy. So the Apennines are the mountains that represent part of a plate boundary, I guess, from the crust going underneath Italy from the west. And the very first geothermal power plant on the planet was Lajarello, which was, I think, from the 1920s, which was developed. And then some locations in Turkey as well. These are conventional geothermal fields. And so most of Europe is not very warm. These contours, or the shading, is high temperatures. And you see areas of high temperature here in dark shading. Interestingly, warm in France, but certainly warm along the Rhine-Graben and in portions of Italy, and certainly in Turkey, which is another plate boundary within the Mediterranean which exists here. So anyway, so it at least explains exactly what's going on. So, since we know something about now the heat flow, then one parting shot, I think, would be to do the calculation to figure out exactly where we got this number. So we, on last Thursday, a week ago, we talked about the relative size of the resource underneath the US, and it was something like 10 to the 7 exajoules. And so from what we know about energy usage, we know that the world uses something like 500 exajoules a year, the US 100. And so if the US is using 100 exajoules, and which is 10 to the 2, then this is enough to last for 10 to the 5 years, so 100,000 years if you can recover it. So it's a huge resource, but it's not really so accessible. Where does the number come from? Of course, you have enough now to be able to work out what that number is, because you know that the energy must equal the volume multiplied by the change in temperature multiplied by the density times specific heat. This is certainly an equation you'd be used to. So this would be the volume of the reservoir that exists. This would be the temperature change between the temperature at depth and the one that you're exhausting it to, which would be surface temperature, 20 degrees centigrade, essentially 1 degree, or 0 degrees, if we're talking about hundreds of degrees centigrade as you go down. Density of rock, we said, is 2,700 kilograms per cubic meter, and the specific heat capacity of rock, which we said was 1,000 joules per kilogram per degree Kelvin. And so that's written out below, and so this is my poor attempt to be able to take this picture of the US. A rough size is a block which is 2,000 kilometers from north to south, 5,000 east to west, roughly. This is kilometers, not miles. It's probably about right? It's probably about 3,000 kilometers at the broadest width of the US, 3,000 miles, which is 5,000 kilometers. And the calculation for this 10 to the 7 was 6 kilometers between 4 kilometers and 10. And so we know that if we, depending on our geothermal gradient, at 4 kilometers and 50 centigrade per kilometer, we'd be at 200 centigrade. At 25 degrees per 100 kilometers per kilometer, we'd be at 100. At 10 kilometers and 25 degrees centigrade per kilometer, we'd be at 250. So I guess I've taken 25C. And so if we do the math on this, then it comes out as this. This was wrong before, I corrected it, but I want to correct it properly. This is 10 to the 7. And so the energy is equal to the volume. The volume is equal to 5,000 kilometers by 2,000 kilometers. So I guess that's 5,000 times 2 is 10,000. So that's 10 million kilometers, square kilometers. The depth is 6 kilometers. So 10 million kilometers is 10 to the 6. 6 kilometers is the vertical depth between 4 kilometers and 10 kilometers. So that's the total volume that exists. The density of rock is 2,700, 2,500, doesn't make any difference. The specific heat capacity is 1,000 joules per kilogram per Kelvin. And say the temperature, if you take an average, so if you go down from 100 degrees centigrade to 250, I guess you could make an argument that the average should be midway between those, so it should be half of 125, so it'd be about 175, right? This I suppose would be 175. So I guess you could do the calculation with 175. Of course, it's 175 degrees centigrade, but we're interested in the change in temperature from the temperature at depth to the surface temperature. So that's the, and it ends up being, if you work it out, it's not 10 to the 22, it's 10 to the, this is definitely 10 to the 7, and so this would be 3 more, so this would be 10 to the 25. I think, I'm pretty sure. And so, yeah, so I didn't, so the area wasn't correct in the previous calculation. So this turns out to be the right number. So this is kind of a number that came out from a relatively famous report. Now 16 years old, I guess, the so-called MIT report. Jeff Tester was the guy who wrote it. And basically what they did was they went through the US. They took the data from whatever available boreholes were present. So if you have a borehole which goes down to some depth and you know what the bottom hole temperature of that borehole is, and you know what the surface temperature is, and this is elevation, then of course you could calculate the thermal gradient from that because you know this bottom hole temperature, and you could also therefore calculate the heat flux if you wanted to, right? The heat flux would be just Q is equal to thermal conductivity, change in temperature with depth, negative sign. This is a negative gradient based on Z. And you could do it that way if you knew what the thermal conductivity was. And we roughly know what that is. We have some ballparks. It's 5 of the order of 1 to 10 watts per Kelvin per square meter. Or in these boreholes, you could just measure the temperature at depth, and you could find out what the bottom hole temperatures were at other depths within here, and make a histogram of those individual components. And so I guess the histogram might look like this. You get the picture. So instead of doing this calculation, you have the distribution of temperatures with depth. So instead of assuming a average value, you can just divide this up into a bunch of layers. And that's exactly what they've done. And if you do that, you end up with a map of the temperatures at 3.5 kilometers depth here, 6.5 kilometers, 10.5 kilometers, because all of these individual boreholes would be different depths, and you have different access to different temperatures, etc. And if you amalgamate these, I guess this is the figure here. If you look at all around the country, what the volume is, the areas that has at 3.5 kilometers, which is 150 degrees centigrade, how much of the area is at 200 degrees centigrade, how much of the area is at 250 centigrade, etc. You can start adding up these individual components. So the sum of the areas underneath all of these histograms gives you the total amount multiplied by the temperatures of these histograms, give you the amount of energy you have at each of these temperatures. And that's given here in exajoules for each of these locations. And if you sum them all up, you end up getting this final value. And this was the value. So I guess I quote, 10 to the 7. So 14 times 10 to the 6 is essentially 1.4 times 10 to the 7 exajoules. So that's where that number comes from. So it's no great surprise as to where it comes from. It's just a simple calculation. So that's probably it for today. I don't know. So I guess we've made the point that we know where on the surface of the Earth we need to prospect for this heat. We know the mechanisms by which it's transferred, by conduction and convection. We know how it's controlled by the structure of the Earth, the plates sitting on top of the mantle, etc. I guess we know 40% of it comes directly from the core and 60% by radiogenic decay. Doesn't really matter to us. But we know the net result of that is a geothermal gradient, which is high in plate boundaries, where we also have the desirable consequence that the crust is all broken there and is highly permeable, so that our relationship for the amount of heat that we can extract by convection, forced convection, works for us, because not only do we have high temperature at shallow depths, easily accessible to drilling, but we can also get large mass flow rates because the permeability is high because the rock is broken up. And so plate boundaries are good for us for those two reasons. They're always moving and deforming and therefore breaking up. Parts within the centers of continents move much less and therefore heal and seal and are not good reservoirs necessarily. And so I guess the focus then of our course is if we know that the heat is there, that it is of a certain magnitude, which is probably big and large enough for us to be useful, the key question that we have to address is, can it be recovered? And certainly on plate boundaries, it's quite easy to recover it because the permeability is high, mass flow rates can be high, and the temperature is high, relatively shallow. Centrally within the crust, for instance, underneath our feet here, the geothermal gradient is less, so you have to drill down deeper to get to any particular hot material. And the permeability of that material is quite low. So recovering it from it by forced convection, by pushing fluid through it, isn't very easy. If we apply very large pressures to it to be able to move it, then those pressures eat up the energy budget because you have to apply energy to pressurize the fluid to be able to get it to move across the system. And there's also a finite pressure that you can apply before you start fracturing the rocks, and that pressure would be when the fluid pressure is equal to the overburden load due to the rock that's sitting above that particular point. And so if you increase the pressure above the in situ stress due to the material above it, you'll hydrofrack it, which might seem at one stage good because you make a fracture, and that's permeability, and you can force the fluid away to the recovery well, which you just follow the fracture, you look at its acoustic emission or little earthquakes that describe the location where it travels, and you drill a hole to intersect it. But the problem with that is that the hydrofracture is a planar fracture with just a face on it, and it's not a very efficient heat conductor. And the heat transfer area on that fracture is very low. So it comes back to the same issue that we talked about when we talked about the EVER problem, is you have a borehole that goes from the inlet to the outlet. It's only a very small heat surface area, which would be the diameter or the circumference of that borehole, which might be of the order of 10 centimeters, 4 inches, something like that, I would imagine. Could be a bit bigger, but it wouldn't be bigger than a foot, for instance. And the only heat that you can get into that is by conduction from the rock around it. And if you work out what that heat flux is, it's relatively small. And so you can make your life better by having a very long section which is in the subsurface. And so on the figure, if you noticed, it's 3,500 meters deep, 25 centigrade per kilometer, so it's probably close to 100 centigrade, as we said, and it's 5 kilometers long. And so the longer the system is, the better chance you have of having a very long residence time for the fluid within that pipe, for it to pick up the heat by conduction, and then come out at the other end at the same temperature as the reservoir. But if you don't leave it with a long enough residence time to pick up the temperature, you'll pump in cold water and it will come out cold. And so that's part of our heat flow equation. Mass flow rate, specific heat capacity, and temperature. If you don't have any of those, you don't have a geothermal system. And so our challenge, I guess, is to make sure that we have all three. So that's kind of where we're going. So next time we'll talk about the thermodynamics, I guess, of geothermal reservoirs. So that's kind of a logical carry on for this. And I guess, yeah, we finished early, so that's fine.